let us take up an example today of generating what are called the symmetry adapted linear combinations, generally referred to as SALC'S. Now, we can take an example to illustrate how we can form the SALC'S by using C3H8 as an example. C3H8 is the cyclopropenyl group. Now this cyclopropenyl group has 3 carbon atoms in a cyclic ring, and each carbon atom is carrying a p-pi orbital. So the 3 p-pi orbitals can combine and generate a delocalized pi system in the cyclopropenyl ring. Let us draw this cyclopropenyl ring structure and see how we can generate the SALC'S from it. Now, the cyclopropenyl ring is basically a equilateral triangle, and we have at each carbon atom a p-pi orbital. This is 1, 2 and the third p-pi orbital. Now let us label the carbon atoms. Let's assume that this is our phi 1, carbon 1, and this is our phi 2, and this is our phi 3, the 3 carbon atoms carrying the 3 p-pi orbitals. Now, what is our problem? Our problem is that how can we use some group theoretical principles to be able to find out how these 3 p-pi orbitals combine and generate what are called the symmetry adapted linear combinations. And these symmetry adapted linear combinations will then be the precursors of the actual pi molecular orbitals of this particular molecule. So this is our problem. Now, as a first point, we need to first of all find out what is the point group of this molecule. So the first step is to find the point group. What is the point group of this molecule? Now you can see this is an equilateral triangle. At the center of this you can have basically a C3 axis passing through the center of this equilateral triangle, and this is a C3 axis because if you rotate if you do a rotation operation of C3, each phi 1 will go to phi 2, phi 2 will go to phi 3, and phi 3 will go to phi 1. So there will be a rotation about for all the 3 carbon atoms, and therefore there is a C3 axis over here. Now besides this C3 axis, we are going to have perpendicular to this C3 axis the C2 axis. So there is a C2 axis which passes through the phi 3 perpendicular to C3. There is another C2 axis which passes through phi 1, and there is another C2 axis that passes through phi 2. Now let us label these C2 axis also. So let us say this is our C21, let us say this is our C23, and this is our C22. Now besides this, that is the C3 axis and the 3 C2s perpendicular, this suggests that there is going to be a D point group for this. Now in fact, with this D point group you also have a sigma h, that means there is a plane of symmetry, and you can do a reflection operation about the plane of symmetry of this molecule. So there is basically a highest force C3 axis, plus there are 3 C2s that are perpendicular to C3, plus there is a sigma h, and this suggests that the point group is D3H. So the molecule possesses a D3H symmetry point group, and because this is a D3H, we can use the character table for the D3H also for this particular molecule. Now before we go into the use of any other aspect, let us say what is our second point. Our second point is that we need to write down a reducible representation which is based on the 3 p pi orbitals in consideration. That means our basis set is basically the 3 p pi orbitals, and we want to see, that means writing down a reducible representation means that we want to see how these p orbitals transform and what are their characters under the symmetry operations of the D3h point. Now let us say, as a third step, we need to then write down what are the symmetry operations of a D3 point group. Let us say D3h point group. We have the identity operation, we have basically 2C3, we have a 3C2, a sigma h, and 2S3 and 3 sigma b. Now you can see that a S3 will also exist alongside with C3, because S3 is nothing but a C3 followed by a sigma h. So because you already have a C3 and you already have a sigma h, so a S3 will also exist, and there will be also vertical planes of symmetry along the C2 axis. So this is a sigma V1, let us say, this is a sigma V2, and there will be a sigma V3. So these are the planes of symmetry. 3 planes of symmetry will also exist, the vertical planes of symmetry, wherein you can do a reflection operation. So when you have the following operations of the D3h point group, you can see how what will be the reducible representation. That means how do we write down the characters for the 3 p orbitals under each operation. Under each is identity, means they remain as such, the p orbitals remain as such, which means the character is 3. Under C3, you see what is happening is phi1 goes to phi2, phi2 goes to phi3, phi3 goes to phi1. That means each one of them is transforming into one another, and therefore the character is going to be 0, because as per our rules, when a particular atom or a orbital moves into another one, then the character is considered as 0. If you consider the C2, let us say, which is a rotation operation by 180 degrees, you find that if you do a C2, let us say a C23 over here, you basically exchange phi3 with phi1. So naturally that character will be 0, but this phi2 remains where it is, because you are doing a rotation C2 operation about the phi2. So phi2 shall remain same, therefore the character will be 1, but because you can see that the p orbital lobe has a different sign, it is a plus sign on the top and a minus sign at the bottom. So when you do a C2 operation, what happens is that this p orbital, that means this p orbital, which is plus minus, if you do a C2 operation, actually gets inverted, so it becomes minus and plus. So this means that the p orbital sign changes when you do a C2 operation. So this shows that the character will be 1, but it will be, sign will change, and this will be minus 1. Now under sigma h, again the same thing will happen, because all the phi1, phi2, phi3 will remain where they are, but because there is a reflection, the plus will go to minus, minus will go to plus, and so on and so forth. So again the character will be minus 3 over here. Finally you have S3. S3 is nothing but C3 and reflection, and basically phi1 will go to phi2, phi3, so this is again 0. And under sigma V, again if you are doing a reflection operation, let's say about sigma V3, phi3 exchanges with phi1, so that net character is 0, but phi2 remains where it is, and therefore in this case the character is 1, because there is no change of sign of the p orbit. So this is our reducible representation, and this reducible representation can be broken down into its irreducible components by simply using the character table of the D3h point group and finding out that how the irreducible representations sum up to this particular reducible representation, and we find that these can be broken up into a A2 double prime and a E double prime. So you have basically irreducible representation which is a singly degenerate, and you have a second irreducible representation which is doubly degenerate. So these are the two irreducible representations which are part of this reducible representation, which is based on how the characters will change when you do the operations of the D3h point group on the p orbitals. Now once we have got this, we need to now get into another important aspect, and that aspect is what is called the projection operator technique. Now that projection operator technique can be used or applied on the irreducible representations that we have been able to find, and then we will be able to generate primarily the symmetry adapted linear combinations for all the three p orbitals. Now let us see what we mean by the projection operator technique. The projection operator technique basically, let us say supposing you want to apply it on, so let's say the projection operator technique. Now this is simply written as, supposing you want to project out P or apply the projection operator technique on A2 double prime, which is one of the irreducible representations which we have found out. Now this is simply some constant 1 by 12 sigma of summation of some character which is R A2 into R operation character. So basically what we want to say is that the projection operator, when this P is applied on A2 double prime, this is nothing but the individual operation which we have considered, that is what will be the fate of phi 1, phi 2 or phi 3 when you perform the individual operation on the basically using the point group D3h, and then multiply it by the character of the required point group required operation, and multiply it with the operation over here. Let's illustrate this point, and so that we can understand what we are actually wanting to say. Now supposing we want to do this, we are basically wanting to let us first of all rub it out so that we need more space over here. So what we are trying to say is that we are primarily wanting to do the following. Let us say you have the following operations. You have is E, C31, C32, then you have C21, C22, and then you have a C23. You have a sigma H, a S13, S23, sorry, S13 and S3, S13 and S3, and then you have sigma V1, sigma V2, sigma V3. So this is S32. So let's just show it once again. You have E, C31 clockwise, C32 anti-clockwise, C21 the first rotation operations, C2 second, third, sigma H, S13 basically this is the operation which is C3 and sigma H, and S32. So basically this is the clockwise, this is the anti-clockwise. So we have the following and then we have the sigma 1, sigma 2 and sigma 3. Now let us see what happens to phi 1, that is this p orbital, as you perform this operation on phi 1. If you have E, it remains phi 1 because that's the identity operation. If you do a C3-1 which is clockwise, so this means phi 1 goes to phi 2, phi 2 goes to phi 3, so phi 1 goes to phi 2, so you have this as phi 2. If you do a anti-clockwise, then phi 1 goes to phi 3, so this is basically phi 3. So you have phi 1, phi 2, phi 3 as you are performing the operation R, that is E, C3-1, C2, this is what is the fate of phi 1. Then you do a C2-1, if you do a C2-1, let us say C2-1, that means phi 1 remains where it is because the axis is passing through the phi 1, so this will remain phi 1. If you do a C2-2, basically phi 1 goes into phi 3 and phi 3 goes into phi 1, so this means this becomes phi 3. And if you do a C2-3, basically then what is happening is you are doing a this is C2-2. So when you do a C2-2, basically you reflect phi 1 with phi 2. So this means we have basically, if you do a C2-2, then you are exchanging phi 1, so I am sorry, this is going to be phi 2, and if you do a C2-3, phi 1 will go to phi 3, so this is phi 3. If you do a sigma h, then phi 1 will remain where it is, so it will become phi 1. If you do a S1, basically it will be doing a sigma h and also a C3. So if you do a clockwise, phi 1 goes to phi 2, so this is what happens. And if you do a anti-clockwise, phi 1 goes to phi 3. And similarly, if you have the reflection operations, if you have a sigma V1, phi 1 will remain where it is. And if you do a sigma V2, then phi 1 goes to phi 2. And if you do a sigma V3, then phi 1 goes to phi 2. So you see what is happening is, you have actually generated what is called a transformation table. So this whole thing can be referred to as a transformation table. And under this transformation, what we have done is, we have actually, if you remember, when we defined our projection operator applying on A to double prime, we said it had two components. One component was that how the phi 1 will transform under the operation R. This is what we have done. We have been able to write down the transformation table, how phi 1 is transforming into what when you perform the operations of the D3h point group. Now, in the second case, you can repeat the same thing by using a phi 2 and a phi 3. So you will get a similar kind of a situation. You will get basically you may end up with a phi, you will get all the transformations that we have done carried out over here will be done. Now the phi 2, if you do a identity operation, it will be a phi 2, this will be a phi 3, and similarly if you do a C3-1 clockwise, phi 2 will go to phi 3, so this will be phi 3, and if you do a anti-clockwise, then phi 2 will go to phi 1. So you can see that similarly if you have a phi 3 identity will remain phi 3. If you do a clockwise, phi 3 goes to phi 1, and anti-clockwise, phi 3 goes to phi 2. So you can see that just like the transformation that has taken place over here, phi 1 will go into either phi 1, phi 2 or phi 3, for all the operations. The same will be true for phi 2 as well as phi 3. That means the transformation table will transform, basically will shows that phi 1 will transform under each operation either as phi 1 or phi 2 or phi 3, and this gets repeated. The same way over here, phi 2 gets transformed into phi 2, phi 3 and phi 1 and so on and so forth, phi 3 into phi 3, phi 1, phi 2 and so on and so forth. And therefore we find that for all the three p orbitals that we have written down the transformation table. Now we come to the second part. Remember, the projection operator PA2 was sigma of some constant 1 upon 12, and you had basically the character of A2 for each operation into the character into the transformation, that means under each operation, that is basically R. So we have taken care of this part. When we do the transformation table, we have taken care of this part. Now the other part is to simply multiply the character of A2 double prime under each operation with this particular transformation table, and then we will be able to get the projection of A2 double prime. Now if you look at the D3h point group table, which will be provided to you in an examination as an appendix, you will find that most of the characters are plus, but excepting the ones where you have a C2, a sigma h and a S3. That means for the first three, the character for PA2 is plus 1, so they will remain phi 1, phi 2, phi 3. But for C21, C22 and C23, the character is minus 1, so basically these will change into minus phi 1, minus phi 2 and minus phi 3. So let's put them in a bracket, minus phi 2 and minus phi 3. Similarly for sigma h it will become minus, and similarly for S1 and S3 also this will be minus. Rest of them will be plus. Now why they are minuses, as we have already shown, that if you do this operation, the p orbital changes sign. The phi 1 will remain where it is, but the p orbital is changing sign. So you have to you have basically the character over here, and now when you have this particular thing, you already have a sign over here, and now you multiply with PA2 the character, and therefore you will find that because the character in the D3h point group for these is also minus 1, so therefore this multiplication will result in a positive integer. Let me just repeat this point once again. We have found out a transformation table by applying the rotation, all the operations, symmetry operations of the D3h point group on phi 1. We were able to find that this is what we got, but we have put a sign, minus sign over there, because if you remember that phi 1 will, if you do a C2 operation, also changes sign, so it will become not phi 1, it will become minus phi 1, minus phi 2, minus phi 3, and similarly in a sigma h, this p orbital will invert sign, so it will become minus phi 1, and so forth. That means we have written down the transformation table by considering phi 1 as well as the changes that will take place on the sign of the p orbital. Now in the next step, we have to multiply this R, which is the transformation table, by the character or appropriate character for each operation for A2 double prime. Now this is, as I said, is in the D3h character table, and we find that all under C2 the characters are minus 1, under sigma h the character for A2 double prime is minus 1, and for S1 and S3 they are also minus 1. So that means when we multiply this by minus 1, rest of them being positive, this whole thing will turn into basically 4 times of phi 1 plus phi 2 plus phi 3. And in fact, if you consider all the three of them, you will again end up with, let us say, basically 4 times for this, 4 times for phi 2, and 4 times for phi 3. So let's appropriately put it phi 2, phi 3. Let's say so primarily what we are saying that one of the symmetry adapted linear combinations that we have been able to find out for the p pi orbitals under the irreducible representation A2 double prime is transforming as phi 1 plus phi 2 plus phi 3. Now, if the form of this SALC, so this is one of our SALC'S. So this is a SALC associated with A2 double prime, and so the form of the SALC is some phi 1 plus phi 2 plus phi 3. If you normalize this will be simply taking the integral of phi 1 plus phi 2 plus phi 3 into square d tau, and therefore you will find that the cross terms will vanish. That means phi 1, phi 2, phi 2, phi 3 will vanish, and the only thing that will remain will be phi 1 square plus phi 2 square plus phi 3 square. These are unity, so it will become 1 by root 3. So the normalized SALC is 1 by root 3 phi 1 plus phi 2 plus phi 3. Let us stop here for a moment.